Welcome back to the lecture series on irrigation systems. In today's video, we are going to discuss about soil moisture constants. If you remember, in the previous video, we studied about the infiltration and important equations. So, in this video, we will be continuing with soil moisture constants. If you closely observe these two pictures, you can imagine why does water behave differently on various soils. On one side, there is a flooding, and on another side, there is a drought. So here, the soil moisture constant plays a crucial role in managing the water in the soil. This constant, it guides agriculture, hydrology, as well as the ecology by understanding how water interacts with the soil and the plants. So what is soil water potential? Soil water potential is the measure of the amount of energy or work required to transport water from the soil to a reference state of pure water at a given temperature and pressure. So in the last video, we studied that water is extracted through two forces, major forces, that is gravitational as well as the capillary forces. So here the soil moisture constant quantifies the driving force or the energy potential required to move water within the soil system. So water has to be moved from the soil to the plant as well as the water has to be moved from the soil surface to inside through infiltration. So this is influenced by factors like gravity as well as the presence of dissolved solutes and also the interaction with the soil particles. So remember the sand, silt as well as the clay when we speak about soil particles. So here you can see the soil water potential equations, that is It is equal to Psi Z plus Is plus Im plus Ip. So what is Ip? That is the total potential, that is the total energy required. And Psi Z represents the gravimetric potential, Psi is the solute or osmotic potential, and M for metric absorption force and P for the pressure due to external forces. So you have to remember few concepts here in understanding the soil moisture constant. One is the field capacity. So what is field capacity or FC? This is the maximum water which is retained by the soil after gravity drainage, usually 2 to 3 days after saturation. So if there is a rainfall today, and if you take into account how much water is retained by the soil, maybe after 2 to 3 days, this we call it as field capacity. That is the maximum water that is retained. We call it as FC. And this is influenced by various soil texture as well as structure, which we studied in the previous series of lectures. And how it is measured? It is measured as volumetric content percentage, which is crucial to study the water availability. In general, the soil water potential ranges from minus 0.1 point to minus 0.3 bars or minus 10 to minus 30 kilopascal. Then the second concept is permanent wilting point, PWP. So what is PWP? So this is the moisture level where the plants cannot able to extract the water. So at this point, plant cannot even, if the plant requires water, it cannot able to obtain even a drop of water, which leads to permanent wilting, or the plant will permanently die. This occurs in places where these drought episodes occurs. Usually the water potential here is at minus 1500 kilopascal, that is 15 bars. Metric potential indicating the plant is under water deficit. So beyond this level, you cannot able to recover the plant. Then variation, this depends upon the plant type as well as the soil type, whereas the loamy soil is around 10% and clay soil is about 20%. And another important factor is available water content. This is very, very important. So we studied what is field capacity, the maximum water retained in the soil, and permanent water wilting point. and beyond this the plant cannot able to recover, and in between we call it as available water content, or the water available to the plant between the field capacity and wilting point is available water content, and it is calculated by a simple formula, that is field capacity minus wilting point. For instance, if we say that the field capacity is at 30% and the wilting point happens at 10% moisture level, and how much will be the available water content, that is 20%. So these factors are key for scheduling irrigation and selecting the crops based on the available soil water, especially for dry land farming or in dry tracts where people always depend upon the rainfall for cultivating the crops. So the texture and moisture constants varies with the soil type. So if we take a soil, sandy soil type, the field capacity is low as the wilting point is low and the available water is low. Whereas for clay, the field capacity is high, the wilting point is high because the pore sizes are very small and the plant cannot able to extract water. So the wilting point is much high and the available water is also high. And another important concept here we have to understand is the soil water retention curve. So here in this diagram, you can see the three types of soil. The yellow one is the clay, then the black is the loam, and the red one is the sand. So as I discussed in the previous slides, you can see the wilting point as well as the field capacity. Suppose if I take the clay soil, so you can see the 4% of volume is released by the gravity, and the infiltration is very less. However, 17% is the available moisture and 28% is the unavailable moisture. So, and if we compare it with the sandy soil, that is the red, you see the infiltration is more. So the water drained is 32% and the water in the WP, that is the volume available moisture, is just 6%. And your loamy soil lies intermediate between these two. So this curve is very, very important. So what is soil moisture retention curve? It shows the water content relative to the matrix potential or matrix suction potential in the soil. And we have to remember a constant called as hysteresis, that is, it is the distinct curves for wetting and drying phases which affect the water availability. Usually field capacity, as I discussed earlier, we will be try to understand it after 2 to 3 days when it reaches the constant point. Then what is the use of this retention curve? It is useful to model water holding capacity, and you can able to estimate soil moisture at various depths. And also you can able to design some IoTs or sensors to assess or to estimate the soil moisture based on the soil moisture potential. Again, modeling can also be done with Van Genuchen equation for precision irrigation systems, as well as you can also use some AI models to estimate or to predict the soil moisture in different areas. How to measure the soil moisture content? It's very simple, as we have learned earlier in our classes. One is the field method, where we employ the tensiometers, time domain reflectometry or TDO for real-time moisture estimation. In lab, we use laboratory techniques like pressure plates and control setups to find the retention points of the soil. And the more precise one is the remote sensing. Satellite data from SMAP estimate the surface soil moisture globally, and you can also understand the available water as well as soil moisture level in different sites or different soils or different regions at a global level. Then data loggers, you can go for IoT or sensors or any type of automated devices based on the concepts of field capacity, permanent wilting point, as well as the available water content, which can be easily linked to the environmental or meteorological parameters, and you can monitor the data continuously using these AI data loggers or any sort of data loggers. Using this, you can go for modeling and you can go for prediction, and it will be useful for sustainable agriculture so that we can enhance the productivity of soil. So what are the applications of these soil moisture constant? As I said, it is important for irrigation management, that too precision irrigation or site specific irrigation management. You can optimize the water use, you can enhance the water use efficiency and enhance the yield. Drought monitoring, which is very, very important because it is unprecedented effect of climate change, and we are going to experience this drought in future, more episodes in the future. So if you have a very good model system, it will help in early detection of water stress or water deficit. So you can take some proactive action. Then land management to prevent soil degradation by maintaining the optimal soil moisture levels. And in summary, soil moisture constants are very essential and need of the hour for sustainable agriculture and maintaining a balanced ecosystem. For this, we have to pursue our researches on AI prediction models based on this soil moisture constant, which is usually ignored in most of the studies. So we can integrate the soil moisture content as well as the meteorological data to develop holistic models and prediction models, and with accuracy for sustaining our agriculture. Thank you.